So we want to talk about numerical solutions of first-order differential equations, and we've looked at the approach, we've looked at the algorithm, and now we're ready to apply it to particular problems. And so let's see how the problems are presented to us. We are given a differential equation in this form: y prime equals f of t comma y. It's a general function, can be nonlinear differential equation, and we are given an initial condition: y at time t equal to 0 is some known value y0. And then we require a solution for this differential equation over some time horizon, starting with the initial time up to some maximum time of interest. So that is typically how the problem is posed. And so now we want to approach it numerically. And so in order to go over this time interval, we think about discretizing that time. And so we want to choose a time step delta t to start the numerical integration. And so we should think a little bit about the problem before we decide what step size we want to use. And so considerations of physical timescales that are involved. If we have ideas as to how rapidly things are changing in the solution, we have some anticipation. Then, of course, for a numerical solution to also have those changes, we will need to respect those timescales. We will need to represent those timescales. We can't have time step size much larger than these physical timescales if these physical processes are to be represented in the numerical solution. Also, there's another consideration of numerical stability of the algorithm that we're using, and so this is something that more sophisticated analysis will tell us how this is to be constrained. All right, so what we do is we are going to choose a step size using these considerations, and then we start integration from t equal to t0 using this initial condition, using the step size delta t, and we will choose one of the algorithms. And so, for example, we have talked about Euler first order, or the improved first order method, which is a second order method, or predictor corrector method. Or there is a whole bunch of other schemes that you can learn about. For example, there is the class of Runge-Kutta methods, or there are lots of other methods too, and they can all be programmed and one can then integrate. So then, of course, the question is, once we have carried out this integration, we have to ask ourselves, how accurate is this numerical solution that we have obtained? And so for answering this question, we can think about a very practical test, very pragmatic approach, where we say that let's use a sequence of step sizes with different delta t's, and we integrate up to the time of interest, and we compare the solution over the time horizon of interest and see whether the solution we're getting is numerically converging. What do we mean by numerically converging? What we mean is that if we were to plot these solutions, the difference between them that are obtained for different delta t's, as delta t's become smaller, the difference between these numerically obtained solutions becomes less and less. And so at this stage, we have to now quantify these differences that are obtained in the numerical solution when we use different step sizes. So the question is, what is the true solution? What is the solution that would be obtained if we have an exact solution? Of course, in general, for nonlinear problems, reason we are using numerical approach is because we don't have a solution any other way. So this practical test of seeing how the solution behaves for different step sizes is a very practical, very useful approach, and we need to quantify this a little bit further. So we want to quantify this numerical error that we have just talked about. And so if we have an exact solution, then of course we can do this very formally. So if there is an exact solution, let's call it y sub e of t. We can take the difference between the numerically obtained solution yn, which is the solution at tn. We take the difference of it from the exact solution at time tn, and this difference is now telling us how much deviation do we have from the exact solution. And so this is a function of time, and so we need to quantify this in terms of having a number associated with it. How big is this error is obviously the question we want to ask. And so that idea of characterizing how big a function is, or how big this time series of error is, we define what we call a norm of this error. So we can define different norms which tell us how big or how quantitatively large this error is. And so there are many norms that you may have encountered. There is a 2 norm, or this is what we can call a root mean square or RMS error, which is simply defined here. A 2 norm is defined as we take the error at every step, we take the square of it, and we divide it by we add them up and we divide by the number of steps we have, and then finally we take square root so that this has the same units as the original physical quantity. 1 norm is defined here, where instead of summing the squares, we take absolute value of the error at every step and we sum them up and divide by the number of steps. So this is an average error when we add the absolute value of the error. So when the error is negative and the error is positive, taking this absolute value means that in this summation they will not cancel. And the same thing of course happens here, because once we have taken square, then the negative thing when it's squared is also positive, so it adds up again. So root mean square does the same thing. So there are 2 different criteria here for error. We can of course also take the extreme error, which is called the infinity norm of the error, which says that let's take the worst possible case. Let's take the maximum of the error over the entire interval of interest, and we can call that as a norm. So these are 3 different norms, and in general, instead of 2 here, if we put a power p and take the 1/pth power of that whole thing, then this would be called a p norm. So we have these different norms, different numbers that we can get, 3 different numbers, and then we can see how big these numbers are. And in a practical application, we have some idea of what is an acceptable error. Does our solution has to be accurate to 6 digits, 7 digits, or many more digits, or 2 digits, depending on what the use of this solution is going to be, tells us what is the acceptable tolerance. So this error will then allow us to see how close to some expected tolerance we have come. All right, so what we're going to apply this to example problems and see how different numerical methods perform.